Today we're going to be taking a look at 7.4 properties of logarithms. The logarithms that we're going to look at allow us to simplify logarithmic expressions into something a little bit easier to work with. In the next section that we get to, we're going to be using these properties to be able to solve equations. So right now, today is just a matter of getting familiar with the properties. The first properties that we're going to take a look at are the basic examples of when we see a log with an exponent or seeing a logarithm as an exponent. These are the two examples that we're really going to be talking about. This first one, when we see an exponential equation, that's because we see a base raised to a power and it has that log as the same power. If you're trying to simplify this and you want to try to figure out what it's going to be equal to, which we are saying that is equal to x, is if it's in an exponential and we can't solve it, what we want to do is we take that exponential equation and we write it as a logarithmic equation. So if we remember from the last section, it was log base b of a equals x is the same exact thing as b raised to the x equals a. This is the example that we have right now, the exponential. So we take our base, which is the b, it's going to become log base b of a equals x. So log base b, which in this case is the b, of what that's equal to, which right now we're saying it is x, but let's see why it's actually x, should be equal to the exponent, which is log base b of x. Well, when we rewrite this to be logarithmic form, we see that we have log base b here along with log base b here. Well, when you have two logs that have the same base, what you're taking the log of should be the same thing as what you're taking the log of the other side, which means x should come out to be equal to x. So what this is saying is that when you have the base and you're raising it to the log with the same base, that those two things really are just going to cancel each other out, leaving you with what you're taking the log of in that exponent. Same thing goes over here. Right now we have a logarithmic problem. Let's see why this one again comes out to be equal to x. It's written as a log. We want to change it from the log that it is into the exponential. So we start off with the base, which is b, raised to the x that we're trying to find. And that should be equal to what we're taking the log of, which is b to the x. Same base means that the two exponents should be the same. That's why this one comes out to be equal to x. So these are some two basic examples that when you see that you have that base that is matching what you're either taking the log of in this example or the base in this one is the same as the base of the log there, that those things cancel themselves out. So let's take a look at these couple examples. The first one, log base 8 of 8, which is raised to the 3x plus 1 power. Well, we really have two ways to be able to simplify this out. One is you could take a look and say which example does it match and follow what we just talked about. The option that may be a little bit easier here is we just have a logarithm that we're trying to simplify and we don't exactly know what to do with it. So we're going to say it's equal to y. Since we don't know what this is equal to, we don't know how to simplify out the logarithm, let's take it out of logarithmic form, change it to exponential. So it's going to be the base 8 raised to the y power, which is what we're trying to find, should be equal to what we're taking the log of, which is that entire thing, 8 raised to the 3x plus 1, which the bases are the same now, which means the two exponents should be the same, so this thing just comes out to be equal to that, which is 3x plus 1. The second example, we're taking the log of something, the log base 5 of 125. We don't know what this is equal to, so let's just say right now it's equal to x and change it out of logarithmic into exponential. So this is going to be 5 raised to the x equals 125. 5 raised to the x equals 125. Which, what number would we raise 5 to be able to get 125? And that would be the third power. So in this case, log base 5 of 125 is just equal to 3. The second option that we would have is we could use this idea here where we see that that base is a 5 and the other number we'd want to try to write as that same thing. So when you see a logarithm that you're trying to actually simplify out, you see that base of 5. Well, if we can rewrite this number that we're taking the log of as that base, we can go through and simplify it out this way. So option number 2 is we rewrite 125, which we just kind of said 125 was 5 to the third, as 5 to the third, log base 5 of 5 raised to the third. That's this example right here. That just means it's going to be equal to 3. And then this third one, 2 raised to the log base 2 of 27. Again, if we don't remember this property on the left side of the screen of how to simplify that out. Right now we can ask ourselves, what form is it written in? Well, it's 2 raised to a power, so that's exponential. Well, we take it out of exponential, write it as logarithmic. So log base 2 of what that is equal to, x equals the exponent, which is going to be log base 2 of 27. And we see the logs are the same, so that means those two things should be the same, and it just simplifies out to be 27. So the idea here is, if you can remember those two properties, remember those two properties. But really, as we went through these 3 examples, it was, we see that it's written in one of the forms, logarithmic or exponential. We can't really solve it that way, so when we have it in one of those forms, change it to the other one. When you get stuck in the one form, you can always go through, change it to the other one, and most of the times that will help you out. The next thing we're going to take a look at is we're going to jump a couple slides, and we're going to talk about this property, which is when we see a number actually raised to a power inside a log. What this is saying is, when you have a number that's being raised to a power, you can take that power and move that power out in front of the logarithm through multiplication. This is really one of the better properties, and this can help us go through to solve a lot of these logarithms, especially some of the ones that we just went through and solved on the previous slides. The first example, log of 10 raised to the 4th. If we want to try to simplify this out, there's no reason to be able to figure out what 10 to the 4th is. We can just see that we have this number that we're taking the log of that has an exponent, take the exponent, move it out in front. So it becomes log, or 4 times the log of 10. And then it's just a matter of saying, well, what is the log of 10? Remember, when you don't see that base there, we can always throw in the understood number, which is 10, and say, what is log base 10 of 10? Which log base 10 of 10, if you remember from the last section, or what we did in the last couple ones, let's switch this logarithm in exponential. We don't know what it's equal to, so right now we're going to say it's equal to x. So it's 10, which is the base, raised to this thing over here, which right now we're saying is x because we don't know what it is, equals what we're taking the log of, which is 10. What number would you have to raise 10 to get 10? Is 1, so this is really 4 times 1. This thing is really that last property that we just talked about, of when you see the base and this here, that just simplifies out to be the exponent, which in this case, since we don't see it, is 1. But again, any times that you see log, that you're taking the base of, that you have the base of a number, that just cancels out to be 1, or simplifies down to 1. Then 4 times 1 is 4. This one, I want you guys to do for homework. We can come back to it tomorrow. Let's take a look at this third one. We see that we have an exponent of 5. We take it, we move it out in front. It becomes 5 times log base 2 of 1/2. And now it's a matter of simplifying out the log base 2 of 1/2. Well, we can try to simplify this one the same way that we simplified this one. We have a base of 2, and we need to try to rewrite this thing as a power of 2. Well, right now, if we have the 1/2, trying to rewrite that as a power of 2, we see that that denominator is a 2, and that is a 2. So this is really close to each other. We just have this in the denominator. Technically, this one is in the numerator. So if we take this fraction and flip this fraction, it can become a 2, which is exactly what we're going for. We just have to say, what does that exponent become? Anytime that you go through and that you flip a fraction like this, that involves a negative exponent. So since we're just flipping that fraction to become a whole number, that's going to have a negative exponent. We're not raising it to any power, so it's just going to be a 1 there. So it's 2 to the negative first, which is the same thing as 1/2. So we can write this one to be log base 2 of 2 to the negative first, which we have another exponent that we can move out in front. And when we put that exponent out in front of the one that we already put it with, since we're using multiplication to put it out in front there, we can just multiply the negative 1 times the 5, and it becomes negative 5 times log base 2 of 2. And this, just like this one, this thing is just equal to 1, so it's negative 5 times 1, which means that just simplifies out to be negative 5. All right, let's jump back to this property. This property is saying that if we have the log of a product, meaning that if we're taking a log of something that is really 2 things being multiplied together, so it could be a big number that we want to break down into 2 things being multiplied together, whatever it is, we can rewrite that as 2 separate logs of those 2 things being multiplied together. So we can break those 2 numbers, the product, into two separate numbers as two separate logs. We can also go the other direction, that when we see that we have two logs that have the same base, we can rewrite it as a single log with just multiplying those two numbers together. The key thing that we see to be able to combine these is, one, you have the exact same base and there is a plus sign between the two logs. So if we want to combine these to be a single logarithm, first thing we look for is we have the same base, so we can combine them. It's a plus sign in between the two. So when we see that plus sign between the two, that means take these two numbers, we can multiply these two numbers together, which when you multiply these two numbers, it's 15,625. Now, to simplify this, what we want to do is say, can we rewrite this 15,625 to be a power of what our base is? Can we rewrite that to be a power of 5? Well, if we looked at the two numbers that we originally multiplied, 25 and 625, 25 is a power of 5, 625 is also a power of 5, which means this number should be a power of 5, which 15,625 is 5 to the 6th power. And using the properties that we just talked about, seeing an exponent, we're taking the log of something with an exponent, we can take that exponent, move it out in front, it becomes 6 times log base 5 of 5, which there's our base of what we're taking the log of same numbers, so that means that that is 1, and it's 6 times 1, that just simplifies out to be 6. We can do the same thing for the second one. We have the same base, 1/3 and 1/3. We are adding the two. That means that we can take these two logs, combine them into a single log, and multiply those two numbers together. 27 and 1/9 multiplied together is 3. So it's log base 1/3 of 3. Now, if we want to try to simplify this down, we see that we have a base of 1/3 and we have the number that we're using is 3. Can we rewrite 3 to be some power of 1/3? Well, just what we did in the other example where we had to take the 1/2 and rewrite it as a 2, now we're trying to take the 3 and rewrite it as 1/3, so going in really the opposite direction. We already see the same numbers, we just have to take this from the numerator down to the denominator. To flip that number, to make it really a 1/3, we just have to throw in a negative exponent. And again, we don't have to raise it to a power, so it's just an exponent of -1. This becomes log base 1/3 of 1/3 raised to the -1st. There's our exponent that we can move out in front. -1 multiplied with log base 1/3 of 1/3. Same thing's happening here, that is just equal to 1 now. So it's -1 times 1, which is just equal to -1. The next to last property that we have is taking the log of a quotient. That's dividing the two numbers. The last example is when we multiply these two. This one is where we divide these two. If you take a look, it looks the exact same thing as what the other example was. The only difference is when you had the multiplication here, you saw a plus sign. Now that we have a division, it's just the exact opposite. It's going to be a minus sign. Same rules apply, is they have to have the same base. And if we see a minus sign between it, we are going to divide those two numbers. Whereas if we saw a plus sign, we'd have to multiply the two numbers. So this example, log base 7 of 49 minus log base 7 of 7. We already have the same base, so now it's just a matter of being able to combine that 49 and 7. I want you guys to finish this problem for homework. The last property that we have is the change of base formula. The change of base formula, this is the one that really allows us to deal with logarithms that haven't been too friendly, which if you think about it, every problem that we've done so far we've been able to do without the use of a calculator. This is the one that allows us to deal with the ones that we're not going to be able to do mentally. This is the one that we can go to now, the calculator. It allows us to use any calculator that uses logarithms. It doesn't have to be a graphing one. What this says is if you have the log of some base, or the log base anything of x, if you can't use that base to your advantage, you can't sit here and try to rewrite that x to be some power for the b. What you can do is you can rewrite this as two separate logs. This time, though, it's not adding the logs or subtracting logs, it's dividing the logs. But it becomes the log of what you were taking the number of goes up top, and then the base goes down to the bottom. Easy way to think about this is your base down here goes to the basement of the fraction. So the base always ends up in the basement of the fraction. And then these two things that they put in the A's for, the A's get to become whatever number that you want them to be. They can be 2s, they can be 5s, whatever number you want it to make it easier on you, which if you think about it, if we're talking about using the calculator, what is the one number that we really want that A to be that the calculator allows us to use? and that's going to be log base 10. So we want to think about changing these into base 10. That's what the calc is going to allow us to use. So we start off with this one, log base 5 of 125. If we want to solve this one, not mentally, we want to use the calculator, use the change of base, we can rewrite this one to be, there's our log base 5 of 125. We can rewrite it to be log base 10, so we don't have to write that base of the big number, which is 125, and that's not meaning the big number here, that means the bigger written number, over log of 5, because there's our base, it's going down into the basement. And then it's just a matter of typing this into the calculator. When you type this in, using the graphing calculators, it will come up with a parenthesis there. You have to close this parentheses. So when you write those out with those numbers, close those parentheses, and that will give us an answer of 3. The other option that you would have is if you could rewrite 125 to be a power of 5, which we did that earlier, we could rewrite as log base 5 of 5 to the third. There's your exponent, move out front. So 3 times log base 5 of 5. There's our same numbers, so this becomes 1. And we get 3, which would be the same thing as we got using the change of base. This one, I want you guys to do as homework. Again, you don't need a graphing calculator for it. You just need any calculator. Write it out, use the change of base first, show that you're using the change of base, and then say what that's equal to. The last problem that we're going to take a look at is a word problem. Seismologists use the Richter scale to express the energy or magnitude of an earthquake. The Richter magnitude of an earthquake, M, is related to the energy released in ergs E, shown by the formula M equals 2/3 log of E divided by 10 to the 11.8 power. See, there's only two examples, or two variables there, M and E, that we need to worry about. In 1964, an earthquake centered at Prince William Sound, Alaska, registered a magnitude of 9.2. on the Richter scale. So the magnitude was 9.2. Find the energy released by the earthquake. So it said the magnitude is M. There's our magnitude of 9.2. All we need to do is fill in that 9.2. So 9.2 equals 2/3 log of E over 10 to the 11.8. It's asking us to find the energy, which would be the E, the ergs, we're trying to find E. First thing we really want to do in a problem like this is get that log by itself. What can we do to simplify this out, which would be getting rid of the 2/3. So you can multiply both sides by 3/2, or you could divide both sides by 2/3. Either way, we would get 13.8 equals the log of E divided by 10 to the 11.8 power, and now it's just a matter of being able to simplify this. Well, right now we're in a logarithmic problem that we cannot solve. We're stuck here, so when we get stuck, what we want to do is take this and change this over to exponential. When we change this to exponential, the first thing we want to take a look at is what is that base, which it is a base 10. So for the rest of this problem, I want you guys to finish this one. This will be the third question for homework tonight, is change this to exponential and go through and finish solving this problem and see what you can get for E.